Let's get right to it. Moving fluids is at the heart of engineering, and pumps are the muscle behind it all. If your pump isn't sized right, your whole system fails. That's where suction and discharge come in, not just jargon, but the foundation of pump performance. Suction is how fluid gets to the pump. Discharge is how it leaves. Get these wrong, and you risk a system that's inefficient, unreliable, or just plain broken. Think of pump sizing like casting the right actor for a role. Too small, and it can't deliver. Too big, and you waste resources. The journey of the fluid before and after the pump matters equally. Mastering suction and discharge is what separates a true engineer from a hopeful tinkerer. We'll break down these concepts, look at the practical math, and see how to avoid common pitfalls. By the end, you'll see why these aren't just terms. They're the keys to moving liquids efficiently. We'll even walk through a real-world example. So, whether you're an engineer, a maker, or just curious, this is essential knowledge. Let's build a mental model that actually works. We'll keep it simple, practical, and focused on what matters. Ready to master the art and science of pumps? Let's dive in. Suction isn't about the pump pulling like a vacuum. It's about creating a low-pressure zone at the inlet. Atmospheric pressure then pushes the fluid into the pump. There are two main setups: flooded suction, where the fluid source is above the pump, and suction lift, where it's below. Flooded suction is ideal. Gravity helps, the pump stays primed, and everything runs smoothly. Suction lift is trickier. The pump must overcome gravity to draw fluid up, risking problems like cavitation if the lift is too high. The difference between these setups changes the energy equation for your system. Flooded suction gives a pressure boost. Suction lift creates a pressure loss. Ignoring this can lead to picking the wrong pump or damaging your equipment. Always start by understanding your suction conditions. Once fluid enters the pump, the real work begins: discharge. The pump adds energy, pushing fluid through the system. It must overcome three main forces: static head, vertical lift, friction loss from pipes and fittings, and outlet pressure if pumping into a pressurized vessel. Static head is the height the fluid must be lifted. Friction loss comes from every pipe, bend, and valve. Outlet pressure is any pressure at the destination. All these add up to the total resistance the pump must conquer. Ignoring any of these means your system won't perform as designed. So, how do you combine all these forces? With total dynamic head, or TDH. TDH is the sum of everything the pump must overcome, measured as the height the pump would need to lift the fluid. The formula: TDH equals total discharge head, total suction head. Discharge head includes static lift, friction loss, and outlet pressure. Suction head includes static gain or loss and suction side friction. Example: if your discharge side is 40 feet up with 10 feet friction, and your suction side gives you 5 feet of help but loses 2 feet to friction, TDH E 40 plus 10, 52, equals 47 feet. That's the number you use to pick your pump. TDH turns a complex system into a single, actionable spec. With TDH and your flow rate, you're ready to find the right pump. It's the key to the whole puzzle. Mistakes in pump sizing are costly. Ignoring friction loss is a classic error. Pipes aren't frictionless, and underestimating this leads to undersized pumps and poor flow. Misjudging suction lift can cause cavitation, where vapor bubbles destroy your pump from the inside. Oversizing the pump just to be safe wastes energy and shortens pump life. The goal isn't brute force, it's precision. Always account for every source of resistance, both suction and discharge. Double-check your calculations, especially for friction and lift. Smart engineering is about getting it right, not just getting it done. Let's apply this to a real scenario: a water treatment plant. We need to move water from a basin 2 feet above pump, to a sand filter 35 feet up. The suction line is short and wide. The discharge line is long with several bends. Friction loss, 1.5 feet on suction, 18 feet on discharge. Discharge, head 35 feet static plus 18 feet friction equal 53 feet. Suction head, 2 feet static, 1.5 feet friction equals 0.5 feet. TDH is 53, 0.5 is 52.5 feet. We need a pump that delivers 500 gallons per minute at 52.5 feet of head. With these numbers, we check pump curves and pick one operating at peak efficiency. That's how you turn theory into real-world engineering.